Bhattacharya. Today I should be doing theories of failure part 2, and today I should be discussing maximum shear stress theory. So now maximum shear stress theory, uh, maximum shear stress theory is basically proposed by Coulomb, Tresca and Guest. Okay, so the theory basically states that failure of a mechanical component subjected to biaxial or triaxial stress. I have explained in my previous lecture what is biaxial stress, what is triaxial stress. So the theory states that the failure of a mechanical component, not specimen, please mind it, failure of a mechanical component, you have to understand this word component. So failure of a mechanical component subjected to biaxial or triaxial stress occurs when the maximum shear stress, according to Coulomb, Tresca and Guest, when the maximum shear stress at any point in the component, it can be any point, at any point in the component becomes equal to the maximum shear stress in a standard specimen of the tensile test. So when any component, when in this component anywhere, if the maximum shear stress becomes equal to the yield stress of a standard tensile specimen, then fracture will take place. According to this, if we see a standard tensile specimen, we assume that there are only one stress, that is sigma 1, and sigma 1 is acting. Now, and at this condition, if we plot a Morse cycle, we see sigma 1, we consider sigma 1 up to there, and sigma 2 is 0 because there is no sigma 2. So if we plot this, we see that the maximum value of the shear stress, tau max, should be equal to sigma 1 by 2. The maximum value of shear stress according to Morse cycle should be equals to half of the maximum sigma 1. This is sigma 1. This should be maximum, the value of the maximum. So if we take this value of sigma 1, if when the specimen starts yielding, that is if when sigma 1 becomes equal to sigma yield in tension, what happens? Then tau max should be equals to sigma 1 yt by 2. From this concept of Morse theory, we could say that. Now, if in a component, according to maximum shear stress theory, we could say that the maximum shear stress is equals to half of the yield stress of tension, that is max, or the yield stress of tension, or the yield shear stress, if the yield shear stress is equals to half of yield stress in tension, that is, if a specimen is subjected to yielding, then yield stress, the yielding shear stress should be equal to half of the yielding test in tension, half of the yield stress in tension. Yielding shear stress, that is yield shear stress, should be half of yield test in tension, half of yield stress. Okay, so if in a mechanical component,
three types of principal stress, sigma 1, sigma 2, and sigma 3 is acting.
We see that if there are the principal stresses are sigma 1, sigma 2 and sigma 3. Now from principal stress to calculate the shear stress, we know that it is given by this formulation. If tau 12 is if the shear stress considering sigma 1 and sigma 2, so tau 12 becomes sigma 1 minus sigma 2 by 2, tau 3 becomes sigma 2 minus sigma 3 by 2, and tau 31 becomes sigma 3 minus sigma 1 by 2. Now with this consideration, we say that we don't know which shear stress, tau 1 2, tau 2 3 or tau 3 1 is maximum, we don't know actually. We basically don't know which one is the maximum shear stress. So for this reason, if we compare shear stress with the yield stress, as we have compared that, we have compared shear stress if tau 1 2 is equals to sigma yt by 2 into factor of safety. If we compare this in place of tau 1 2, we place this value of sigma 1 2. So that is we replace shear stress in the form of principal stress. So if we write in the value of tau 1 2 over here, we get this 2 and 2 cancels out. Now we get this form sigma 1 2 minus sigma 2 is equal to sigma y2 by factor of safety. So similarly, sigma 2 and sigma 3 get sigma y2 by factor of safety. Now if we come over here, if we come and write like this, we could see then it becomes sigma 1 2 is equals to sigma yt if the tau 1 2 is maximum. If tau 2 3 is maximum, then we could write this. If tau 3 1 is maximum, we could write this. If tau 2 3 is maximum, we could write sigma 3 minus sigma 1 by sigma yt. So this is the considerations. Now this all we have considered for tension. Now the same thing is applied for compression, which we could see that if sigma 1 minus sigma 2, instead of yc we have represent by y, in place of yc we have represent by yt, we have represent yc. So sigma 1 2, that means if we considered shear stress tau 1 2 is equals to the maximum shear stress in compression, so we could compare it for the compressive load sigma yc, then sigma 2 minus 3 is equal to sigma yc, and sigma 3 minus 1 is equal to sigma yc. Because standard specimen in tension, so yield stress can be generated, and standard tensile space in compression also yield stress can be generated. For this reason, for compression we have plotted this, where we have just replaced the sign. Now if we want to generalize the formulation, so it becomes like this: sigma 1 minus sigma 2 becomes plus equals to plus minus, because both tension and compression this can be possible. Sigma 2 minus sigma 3 is equals to plus minus sigma yt. Sigma 3 minus sigma 1 becomes equals to plus minus sigma yt. Now we have to see that this is the general formulation of maximum shear stress theory. So based on this, the main criteria over which we base that the maximum shear stress, which is equals to the diameter, is equals to half of the maximum stress in tension. So this is the basis of this principle. Now we should be going for the design, that is the safety region of safety. We should be discussing the region of safety now. Now if we plot the region of safety for biaxial stress, we could see that first, because biaxial stress is there, then the principal stress sigma 1, sigma 2 and sigma 3 should have to be 0. So from this consideration we take sigma 1 plus sigma 2 is equals to plus minus yield stress, because sigma 3 is 0, and therefore what happens, sigma 1 it becomes equals to either sigma 1 becomes equals to plus minus sigma y2, or sigma 2 becomes equals to plus minus sigma yt. Okay, now either sigma 1 is because if sigma 1 minus sigma 2 is equals to plus minus sigma yt, so you could write that sigma 1 is equals to plus minus sigma yt, or sigma 2 is equals to plus minus sigma yt. Now we prepare a coordinate system. Over here the x-axis is taken as sigma and the y-axis is taken as sigma 2. The x-axis is taken as sigma 1, the x-axis is taken as sigma 1, and y-axis is taken as sigma 2. Now the first quadrant, you see all the sigma 1 and sigma 2 is positive, and the second quadrant we could see that the sigma 1 is positive. The second quadrant we could see that the sigma 2 is positive. The sigma 1 is negative and sigma 2 is positive. So, and the third quadrant is, we could see that both are negative, sigma 1 and sigma 2 both are negative, and the fourth quadrant we could see that the sigma 1 is positive and sigma 2 is negative. Now based on this we draw a figure. So we draw a figure like this. So this is sigma yt for sigma yt. Now we could plus minus, as because plus and minus sigma yt is given. So for sigma 1 we plot the value of sigma 1 plus sigma yt, and here up to sigma yc. plus YC means compression, so we just change the value, change the name from YT to YC to minus. And similarly for sigma 2 also, we take the positive value as of sigma YT positive and the negative value is taken as the sigma YC compression. Now we just make a boundary of A, B, O, we make a boundary of A, B, C, D, E, F, A. Now this is the boundary. If any coordinate, if the stress, if the value of the stress sigma 1 or if the value of the stress sigma 1 and sigma 2 lies within this area, within this margin, then the design is safe. If it lies outside this, if suppose this value of sigma lies over here, the coordinate of sigma 1 and 2 lies over here, the region is safe for design. But if you take any value outside this region, it could not be considered as a safe design. And this region sigma 1 and this line A to F is represented by sigma 1 minus sigma 2 is equals to plus sigma YT, and D to C is represented by sigma 1 minus sigma 2 is equals to minus sigma YT. So this is the region of safety. If anywhere you could design, as a designer you could take anywhere, you could design the value of the sigma 1 and sigma 2 anywhere, but if you go outside this boundary, if you go down outside this boundary, then the design is not safe as referred by the maximum shear stress theory. And we could conclude that the maximum shear stress theory is obeyed by the ductile materials in comparison to brittle material, and the experimental results are also provided a good matching for the maximum shear stress theory. That's all ends from this part 2 of theories of failure. Thank you. Have a good day.